In this video, we are going to discuss multiple substrate reactions. Now, it's important to appreciate that we spend a lot of time talking about Michaelis-Menten enzymes, generally because those are the simplest, and those involve an enzyme that binds one substrate and converts it into one product. So it's a very simple reaction. However, most enzymes bind two substrates and convert those two substrates into two products. Their kinetics is much more complicated, but let's look at an overview of some catalytic strategies for multi-substrate reactions catalyzed by enzymes. We can divide these types of reactions into two general classes, sequential reactions and double displacement reactions, also called ping-pong reactions. Sequential reactions we can subdivide into ordered sequential or random sequential. In ordered sequential, the enzyme binds the substrates in a defined sequence. So it will bind one substrate always, this one first, and then it will bind the second one in a very particular order. In sequential random binding or sequential random kinetics, the enzyme can bind either of the two substrates first or second. It can bind them in any order. And then double displacement or ping pong mechanisms are a little complicated. It binds one substrate, as we'll see, converts it to product, and then binds the second substrate and converts it to product. So let's take a look at these binding mechanisms for sequential reactions and ping-pong reactions. Let's start with sequential reactions that are ordered. We generally illustrate these using what's called a Cleland notation. And let me kind of show you what we're looking at here. First of all, we start with just the enzyme, just a free enzyme, and reactant A. The enzyme will bind reactant A first to form an EA complex. Then the EA complex is now capable of binding the second reactant, reactant B, forming an enzyme AB complex. The enzyme then converts the reactants into products. Let's call the products P and Q. So we have this enzyme PQ complex. The enzyme then releases the products in a defined order. It will release product P first, leaving an EQ complex, the enzyme in the second product. Then it will release that second product to regenerate the free enzyme. Let's take a look at a reaction that follows the ordered sequential kinetics. This reaction is catalyzed by lactate dehydrogenase, and lactate dehydrogenase binds two substrates. It binds pyruvate and NADH. It converts pyruvate into lactate and NADH into NAD+. So this is an oxidation reduction reaction. Let's look at this using a Cleland notation. We start with the free enzyme. The enzyme then binds to the NADH first. So they always bind in this particular order. The enzyme NADH complex is then able to bind pyruvate to form the enzyme NADH and pyruvate complex. Our reactants or substrates are then converted into products, lactate and NAD+, which are bound to the enzyme, and then it releases the products in a particular order. Lactate dehydrogenase releases lactate first, and then NAD+ second to regenerate our free enzyme. Now, one thing that is interesting to note about these, generally when the enzyme binds the first substrate, the enzyme will undergo a conformational change which produces or opens up the binding site for the second substrate. So that's how the second substrate is not capable of binding until the first substrate is already bound. That causes the conformational change which allows the enzyme to bind the second substrate. Let's look at our second type of multi substrate binding. This is sequential random binding. We start with our free enzyme, and the free enzyme can bind either reactant A or reactant B. It can bind either one first. If it binds A first, then we have the EA complex, which is now going to bind B, or we could have the E enzyme reactant B complex, which then can bind A. So the binding site for both substrates is available and does not depend on the other binding first. Ultimately, we end up with an enzyme EA complex, so the enzyme is bound to our two substrates. The enzyme then converts the substrates into products. Let's call it P one product and Q the other. So we have this enzyme and product complex, and then it can release the products in either order. It could release product P first, or it could release product Q first. Then it would release our second product, ultimately regenerating our free enzyme. An example of an enzyme that follows random sequential binding or random sequential kinetics is the enzyme creatine kinase. Creatine kinase has two substrates, creatine and ATP, and it transfers a phosphate group from ATP to creatine to form phosphocreatine, and in the process ATP is hydrolyzed to ADP. So looking at a diagram of this, we see that we start with just the enzyme, and the enzyme can bind either ATP or creatine first. So the binding sites for both of these are available. So either one could bind in any order. Then the other substrate would bind, and of course you end up there with the enzyme and then a creatine ATP complex. The creatine and ATP are then converted to the products, phosphocreatine ADP, creating our enzyme and product complex, and then the products can be released in either order, the phosphocreatine and then the ADP, or the ADP and the phosphocreatine, regenerating the free enzyme, which now can catalyze another reaction. And the final mechanism for a multi-substrate enzyme that we want to look at is what's called the ping pong mechanism or ping pong reaction. In this case, you start, of course, with the free enzyme, and then one of your substrate comes in, let's call that one A, and you form the enzyme A complex. So the enzyme binds to that substrate. A is then converted into product, let's call that P. And in the process of converting A into P, the enzyme is covalently modified. So maybe a functional group is transferred from A to the enzyme. And so you end up with this, we'll call it FP complex, where F indicates the modified enzyme. So not the free enzyme, but the modified enzyme. And P is the product. So then the product is released, and you have this modified enzyme. So the enzyme is modified with some functional group, which came from A. Now our second substrate comes in, and we form the FB complex. B is converted into our second product, Q, and in the process, the enzyme transfers that modification to the substrate B to form Q. So now you have, in the process, you have the initial enzyme and Q complex. When Q is released, then you regenerate the free enzyme. So let's look at this in a little more detail because it's a little more complicated than the others. Let's use an example of aspartate aminotransferase. This is an enzyme that follows this ping pong mechanism. And what it does, it binds aspartate and alpha ketoglutarate, and it converts aspartate into the molecule oxaloacetate, and it converts alpha ketoglutarate into glutamate. Okay. In the process, notice what happens here. Aspartate is converted to oxaloacetate. In the process, an amino group is transferred from aspartate 2-alpha-ketoglutarate. So this amino group is transferred from aspartate to alpha-ketoglutarate, forming glutamate. Okay, so let's take a look at this. We start out with our free enzyme, okay, and then aspartate comes in. Aspartate binds to the enzyme, so we have our enzyme aspartate complex. Then the amino group from aspartate is covalently transferred to the enzyme. So the enzyme pulls an amino group off of aspartate, converting aspartate to oxalate. So you end up with a modified enzyme product complex. The oxalate is then released, but you still have the enzyme covalently modified with that amino group. So the enzyme holds on to that amino group after it releases the oxaloacetate. Then alpha-ketoglutarate comes in and binds to an active site nearby. The enzyme amino group complex, the enzyme amino group modified enzyme binds to alpha-ketoglutarate to form this complex. Then the enzyme transfers the amino group to alpha-ketoglutarate. So the enzyme now no longer has the amino group on it, so you just have the regular E for enzyme. And now that the alpha-ketoglutarate has accepted the amino group, it's been converted to glutamate. And so you have this enzyme glutamate complex. The glutamate is then released, and you have your regenerated or original enzyme. So be sure you're familiar with these types of mechanisms, and also as we progress and look at some new enzymes, see which enzymes kind of follow these types of binding. See if you can identify this and relate these binding mechanisms to the enzymes that we study in the future.